Hi Sven. So in one of our videos, we talked about how an interferometer works and how you use it for the ESTIA SELENE guides for distance measurements. But there was also a bit of history that led to the decision to use interferometers, and you could in theory also use other systems, right? So could you tell us a little bit more about that?
Yes, absolutely. So to get into why we did what we did, I think I will first spend 30 seconds on what we have to achieve, then a quick explanation on how the mirror setup works, and then an explanation on how we ended up where we ended up. So just as a small reminder, our instrument relies on this elliptical guide, where you have the ellipses, you have the two focus points, and then somewhere in the middle we have this guide section. And basically our beam is reflected from one focus point onto the mirrors and then to a second focus point. This is a two-dimensional thinking. Then we have to do the same basically to achieve the third dimension, but we'll leave this sketch two-dimensional just so we can remember how it works. The fundamental problem here is even if we have a perfect focus point here, we want to have a very narrow tolerance here. So we want to have a 60 micron width after two of those subsequent systems. Not after this, but after another one as well. So basically what we have to achieve, so that's the one part. Then additionally I have to mention that those focus points here, they are some 12 meters apart. 12 meters, and basically we could make an infinite long mirror in between, but by the concept of, by how the neutron reflection on mirrors works, we are limited to the middle 7.2 meters. So that's our actual mirror length. Now, to achieve this very narrow tolerance, we need to produce short and fairly exact mirrors. So we have this subdivided. And this needs to be aligned very precisely on some kinematic mountings, which are here on the back. And they again have precision tolerances of some roughly 1 micron for the most precise kinematic mounts. And of course, you also have to measure that. That leads us to the concept to the measurement concept. So I can quickly draw that up. So we have now, if we take the side view, we have a mirror which looks basically like this. If we would go to the view that you would have from the front or the back of a Selene guide, the mirrors would look like this. So you have the two dimensions. This represents one surface of this ellipsis, and this represents the other surface. If we put it down like this, we end up with something like this. That's for the first beam path. So basically, with that, we can have this reflection in 3 dimensions, and basically the general concept of the instrument is to have 2 beam paths. That means we just have the option to integrate a second one of those on top. And that would then also mean we have this thing here. So that's our basically complete beam. And as I described, this is not one section, but these are many mirrors behind each other. The lines are just representing the fact that there are separations. It's 15 mirrors in total. Good, that's what we have. Now we somehow have to measure where those mirrors are. So we have to, with each of these mirrors here, we have to be able to translate parallel to the beam so that we can bring the mirror into the beam, and we also have to align the relevant angles, and we have to be able to measure that. We have a total distance of 7.2 meters, which is a huge distance if you want to have basically this mirror here aligned normal to the surface of this board within a micron or 5 microns relative to this one. That's basically beyond what you could do with any conventional means used in precision machine building or whatever. So we thought about an autocollimator system, basically putting a laser far away, putting a light on, and then putting a camera back at the source, and then you would see how much the light that comes back deviates from the source, and from that you could say how much the angle is off at least. Problem is, we are in a crowded guide hall, so autocollimetry is off. We have to have something on that system. The next best thing we looked into was interferometry. That's basically that the concept is described in another video. There we figured out that usually interferometers are relative distance measurement tools. That was an issue until we actually found a company that provides absolute interferometry system. That's somewhat expensive and the measurement time is fairly long, but in general you can put an interferometer in front of this here, and then you have a measurement that is precise enough. Then the next problem that you face is that you somehow need to have a base for this interferometer. It has to be sitting on a position that is known, that is very stable. And with the interferometer, you cannot, so basically with the interferometer you have to reflect your light back into the optics where the light is coming from. So you cannot just place an interferometer close here and check up all the guide, but you have to move along the guide with the interferometer. So said, done, we built basically a carrier around this optics that looks pretty much like this. The optics is mounted in a way that it can actually move the translations and rotations that it has to. And on the carrier, we then basically, so the carrier here looks a bit like this. Like this. So basically now the carrier has an opening to one side that is relevant, and on this opening we build a cart basically that is on rails here and here conceptually, and that has some lasers on it or an interferometry system that can reach basically those positions and those positions. Something like this. So said, done, fairly simple. For the horizontal mirrors, however, the situation got a little bit more dire because when you look at such an opening, for example, you don't only have the mechanical problems, but you also have radiological problems. Meaning, if you come from a focus point here and you want to go to a focus point here, your neutrons go into all directions. And you really want to avoid neutrons flying through straight here, because those are the fast ones, those are going to be safety issues downstream, those are going to be measurement quality issues because they create background. So you really don't want to have them downstream. So therefore we had to build in some collimation blocks in the middle of this carrier. That it's copper blocks which basically avoid the direct beam going downstream. This, however, made it impossible to just add to the card a different lever here and to have those these beam paths going up and down from here. So a direct measurement of the horizontal mirrors was off topic very quickly. We had to think about different solutions. The first solution was to build such a thing, but to make it extractable, so basically to move it back or move it up. But then again, you have additional moving parts for the instrument, and with the system working in high radiation, vacuum, and low maintenance accessibility, you really don't want to have too many moving parts. So we had to think further, and therefore we started building basically a concept where we have a laser beam coming from here, going to a retroreflector, and then going all the way back to your collimator. And this again, of course, we would then build twice, something like this. Something like this. So you would come from this collimator, retroreflector, and then you would have basically an indirect measurement of those horizontal mirrors by the vertical ones. The same thing we do for the top mirror, but I'm not going to draw that for better visibility. And so therefore we have a method with which we can measure the position of those mirrors without actually interfering with this zone where we don't want to have additional parts. Of course, this direct measurement is more precise, more reliable, but based on the kind of experiments, I can talk about this in another video, we have a little bit higher accuracy requirements on these mirrors anyway than we do have on those ones, and therefore it's okay. And therefore we can live with a little lower precision here. Okay, so that's basically the general system. So said, done. There have now been some additional issues. So the concept that we have here, that works perfectly if you have this mirror which is perfectly perpendicular to the incoming beam. But the problem that we face is we don't have a straight mirror, but we have a elliptical mirror. So when we again draw the elliptical mirror, we have the focus points. Now we take the bottom part away because that's not relevant because there we don't have mirrors, but we remember it. Then we end up with something like this. Now we have on the bottom we have this straight surface where we have a laser on. And what we do is we have this laser beam coming from here, going to the middle, and the beam is directly coming back into the collimator. Everything is perfect. When we go to the side, however, we have this collimator here, laser beam goes straight up. Now we remember we have a curved mirror, so the laser beam goes back here and wherever. So that doesn't really help. And on the other side, we have the same story. Laser is here, beam goes up, beam goes away. So that means the system that we worked on now that completely failed, we cannot use it in the first place. But if we think about this system in a bit more, then we thought about the system a bit more. So basically, I'm going to draw it again. Elliptical mirror, focus points, straight surface, representing the metrology card and everything it does. So one other setup that one could think of is you can look for an angle. So basically what those mirrors do is we have one mirror that is parallel. Let's take this middle mirror. This is parallel to our reference surface that we have down here. And then you have a mirror on the very end. This mirror clearly has an angle. But this mirror, let's take the centers, clearly also does have an offset. That's delta y. Let's take the delta y because then we look at those mirrors. So, and there, that means if you want to keep all your optics tools on this line, then you can say I put my collimator a little bit like this, and I put a retroreflector a bit like this, and I make a beam that goes to my mirror, goes to the retroreflector, and goes back to the. That's very straightforward so far. But there is actually an angle where this delta y and this angle alpha compensate each other out. So I just made it the wrong way around for this example, sorry. So basically the retroreflector in this case would be here, the collimator would obviously be here. So if you move the same system, I'm just going to try some help for the sketching. So if you move this whole system here, you have again your collimator here, your retroreflector here. You're still coming in under the same angle that you would hit here up here. So you would still hit up here. But now what you do is you have translated the mirror a little bit down. That means under the same reflection angle that you would have here, you would hit next to the retroreflector. But now that also the mirror angle changed, now that we have this alpha, actually what you get is a reflection back into the retroreflector for this place as well. What we have to know about retroreflectors is they really throw back the light into the direction where it's coming from. So they're not really like mirrors where the light goes where incoming angle is equal to outgoing angle, but it really is, it's the same direction and not the mirror direction. So therefore, we can work with this option here. That was quite a success when we realized that that works. So much so good, problem solved, almost. We have a second situation. So when we think about the other mirrors, they are here, that's the other end. We play the same game one more time, different color maybe. We have this position. We again have the collimator on the right side and the retroreflector on the left side. We would have this reflection point. We go up here. So up to this point it really works. But now what we have on this side is actually when we hit this surface, assuming the mirror would be parallel again, then we would come down somewhere here next to the retroreflector. So that's already a no. But then the mirror is on top of that, then our alpha is on top of that tilted like this. So meaning from here, the actual beam that comes down ends somewhere here, far away from where it has to go. So that's then in this case doesn't work. Yes, so much for that. So problem was not solved at this point. What we ended up doing at the end is, I'm going to draw just a small top view of it. We built our metrology card system, and basically we, as close together as we managed to do, built a reflector, a collimator reflector couple for one side and a collimator reflector couple for the other side. So when you look at the metrology card, you will see two of those beam paths, and that's exactly what we need. We need one system for one side of the guide and the other system for the other side of the guide. Now there's just one more thing to say about this system, I think. With all this kinked out, or worked out, we realized that we are far off the tolerances that we want to achieve. So we want to end up in the single microns here. That means we need to, if we take such a mirror here, that means our alignment of this mirror and all the errors and deviations that come with it, and also the alignment of the metrology card and all the errors that come with it have to be smaller. And of course, if you want to control a system, you want to be able to measure some 5 to 10 times more accurate that you want to adjust. Otherwise, you cannot give reasonable commands to your adjustment system. So when we talked about this metrology card, that's a fairly crude oversimplification of what we did at the end. So we were looking into different ways on how to move this system on the reference or on basically on these precise surfaces, and how to machine those surfaces. And I don't know, do you want to take this in this video, or do you want to make a separate video about this?
I think we will take a separate video about that. And in some other related videos, we might maybe also be able to look at the real parts that they have described so eloquently on the whiteboard so far. So thanks a lot, Sven. I think we leave it like that. Thanks for the great explanation. And we continue with another video.